All right, so today's lecture, we're going to be talking about numerical integration, in addition to reviewing some of the subjects that we covered in the previous lecture, and we'll see exactly how and why we use this concept of trying to approximate integral expressions as might appear in, let's say, the weak formulation of a given boundary value problem. We'll see why it's not so convenient to have manipulated our expression for equilibrium into this integral statement, because obviously now we have to compute all of these integral expressions. And it turns out there's quite a number of them that we have to evaluate, which is really contrary to the whole idea behind the finite element method as being this semi-automated procedure or even entirely automated procedure for solving these boundary value problems. If we, at the end of the day, we still have to carry out these integrals, what was the point? I still have to go and, work out the integrals, presumably by hand or however I would do it, if I'm trying to do it analytically. So that's just not a tractable thing to do. We need a different way of evaluating integrals in an automated way that ideally can be done in a way that's scalable and efficient and, is something that a computer can do. So that's where this notion of numerical integration comes about, and we'll see exactly how that comes into the picture, at least in the context of finite element methods. But first, a brief overview. Let's see, we'll talk about why we need this thing. What exactly is numerical integration? How do we actually achieve it? What are some specific methods for carrying out numerical integration, and some of the potential benefits of that, as well as not just a perspective of how to carry out integration of functions in one dimension. We'll also see that this concept can be generalized to the case of 2 and 3 dimensions, which is particularly important once we move on to the subject of continuum finite elements and trying to analyze these 2 and 3 dimensional problems in mechanics. Okay, so a little bit of background. Here's what we covered in those previous couple of lectures that we discussed. The recorded lectures from last Wednesday and Friday discussing aspects of approximate solutions to boundary value problems as posed through this weak formulation of a given boundary value problem. And not just that, but coming up with approximate expressions for equilibrium, seeking some approximate solution expressed perhaps in terms of a finite number of basis functions. So the lecture from Friday talked about a particular choice of basis functions that can be used to express or represent some function as just a finite set of values, which we interpolate using these specialized functions, basis functions, which themselves are nothing more than the so-called finite element basis functions, or these hat-shaped functions, kind of funnily defined. But the advantage of these things, there were several, was that they had this property of compact support. In other words, any one of these particular basis functions associated with a given node in our finite element discretization has only non-zero value over the patch of elements to which that particular node is connected. So for example, this finite element basis function denoted phi3, as shown in this figure highlighted in orange. That function only has non-zero value over this patch of elements connected to node number 3 with coordinates x3. And the associated nodal value of the displacement at that particular point, denoted u3, it basically corresponds to the coefficient that multiplies this function when we come up with some linear combination of these basis functions to construct some interpolated representation of this actual displacement function u as a function of x. So we can come up with an interpolatory function that actually passes through these discrete nodal values or nodal unknowns, the things that we're solving for, to come up with this piecewise representation of a function that, despite the fact that it's not exactly a smooth function, it has these kind of discontinuous derivatives at the nodes, it actually otherwise does a pretty good job of representing fairly arbitrary functions that are nonetheless continuous, an essential requirement for compatibility. All right, so we came up with these finite element basis functions. And we came up with these interpolated representations of these discretely represented displacement fields or solutions to these candidate boundary value problems. And we could take this particular choice of basis functions and this particular discrete representation of a solution field, and we could plug it in directly to our weak formulation of the elasticity boundary value problem. So what that would look like is something where we have some candidate solution for our displacement field expressed as some linear combination of these finite element basis functions, where the unknown coefficients u sub j are just the nodal values of the displacement at these discrete nodal positions. We could also come up with an expression for some arbitrarily chosen test function, or if you like, this test function could be interpreted as a virtual displacement field, which has a similar representation expressed in terms of these discrete virtual nodal displacements, the v sub i's, and also expressed as this kind of linear combination of the finite element basis functions, the same set of basis functions. We could take these two discrete representations for our trial displaced solution field and our virtual displacement field and plug them into our weak form expression of equilibrium, which has to be satisfied for any arbitrary choice of test function or any arbitrary virtual displacement function. We could do a little bit of turning of the crank and some mathematical manipulations to re-express this integral expression in terms of an equivalent system of equations consisting of a discrete number of unknowns, those being the nodal displacements, denoted u1 through un number of nodes, the total number of nodes in this problem, and entailing a discrete number of equations. Having the same number of equations as we have unknowns, we can invert that system of equations to solve for the nodal displacements. And of course, you're familiar with that process because that's exactly what we did early on in the class, and that was the subject of the first homework assignment. So this should all look rather familiar to you. The end result is basically this system of equations, but we've gone about deriving it in a slightly different way than the way that we derived it at the beginning of the class. Instead, we went through all these extra machinations of converting a given statement of equilibrium of a structure into an equivalent strong formulation of equilibrium expressed as a pointwise statement in a differential equation. We manipulated that further into the weak form, this integral expression, and then we introduced this approximate representation of the solution fields in order to come up with this final result. But it's nonetheless equivalent. So we went through some additional hoops to get here. But now you'll probably see a little bit of a problem here. Notably, these expressions that I've constructed for the individual entries of this matrix, which again is nothing more than the stiffness matrix, the thing that we kind of described as being this relationship that establishes how individual forces that show up at the nodes of this particular structure are related to incremental changes in the displacements at those nodes. That's basically what the stiffness matrix tells us. It gives us this incremental relationship between small changes in applied forces at the nodes to small changes in the displacement at the nodes, with the individual coefficients of this matrix being basically characteristic of some kind of force per unit of displacement. That's the units. So in other words, we have this expression for this stiffness matrix, and we have a vector of externally applied forces, which are really kind of equivalent to forces that would be applied at these discrete nodal locations as well. That's kind of the vague interpretation of them. But nonetheless, both of these expressions entail computing these integrals over the entire length of the structure. Now, this is kind of where things get hairy, because certainly we could go about computing some of these integral expressions that involve derivatives of the nodal shape functions with respect to x, products of those shape function derivatives integrated over the domain in order to come up with these individual contributions to the stiffness matrix. But we have to take all these integrals, which is not nice. Obviously, if you have a lot of these different entries, and potentially as many entries as you have unknowns squared, then that's a lot of integration that you have to do, which is not something that you want to spend your time doing. So The goal of this lecture is to really come up with an alternative way of evaluating these integral expressions that show up in these particular expressions for the stiffness matrix and the vector of applied external nodal forces. And we'll see that in some ways, we rederive all the expressions that we had come up with early on in the class to express things like what's the stiffness matrix, not of the entire structure put together, but maybe what's the stiffness matrix associated with an individual element, a single element inside of this structure as a whole. And we can find that coming up with the stiffness matrix of the structure as a whole is no more complicated than simply coming up with the stiffness matrix of individual elements and then patterning them together in this sort of assembly process. And that might look something a little bit like this. Conceptually, if we took this particular example of a very simple one-dimensional structure and a uniaxial rod, and we cut this structure up into two elements, separated by these three nodes, we could think of computing the different entries of the stiffness matrix, where those indices of this stiffness matrix might be indexed over I and j, ranging from 1 to the total number of nodes in the structure. Each one of these individual entries of the stiffness matrix is determined by this integral expression, the thing that we had on the previous slide. However, we could carry out this integral over the entire structure all at once, or we could make the problem a little bit easier and just say, let's break up this integral, and rather than integrate over the whole length of this structure, we'll treat it as two separate integrals. First, an integral over the first element between x1 and x2, and then another integral defined over x2 to x3. And the summation of those two integrals basically gives us the same integral thing over the whole domain of interest, but we can actually carry out these integral computations over these individual elements much easier, as we'll see in a moment. So the overall idea here is that if we wanted to compute the stiffness matrix entries for this global system of equations that we're trying to set up and solve for the unknown nodal displacements, we could pose it in this format, or more simply, we can say assemble or kind of sum up all the different contributions to this integral from each individual element, pattern them together in the appropriate sub-indices of this resulting array. And you can visualize that and interpret that process as being basically just this statement. Compute the so-called global stiffness matrix of the structure as a whole as the summation of individual contributions to the stiffness matrix taken from all the individual elements in the structure, for however many elements there might be. And the individual contributions might look something like this. Just integrate this stiffness expression involving the product of different nodal shape function derivatives taken over the domain of integration corresponding to that particular element of interest. So we can make the problem slightly simpler by doing the integration in this element by element fashion and then assembling all the individual contributions at the end. But still, we haven't worked around this problem. How do we actually compute these integral expressions over these individual elements? In general, if we have relatively simplistic expressions for the nodal shape functions or the nodal basis functions plugged into this expression, maybe it won't look so bad, but we won't know. And in general, if we have some funny looking basis functions chosen for the nodes, I've given you an example of what these basis functions look like, assuming strictly piecewise linear interpolation of these nodal positions. But there are certainly other options that we could choose, such as perhaps defining elements that consist of not just two nodes defined at the ends of this particular element, but maybe you could think of an element that consists of four nodes, and this particular element might have some interpolated representation of this displacement field local to that element that is expressible in terms of maybe a similar kind of setup here, where the individual nodal displacements are really nothing more than these four discrete nodal values, but we would want to come up with some smooth interpolating function that passes through all of these 4 different points. So a total of 4 nodal basis functions would we have to construct in order to actually interpolate these different values. And certainly, in order to do that, we would need something more than simply a linear function to pass through all of these different points. We'd need some higher order polynomial. And nominally, we would need as many orders to that polynomial as we have these discrete unknowns that we would have to interpolate. So in that sense, coming up with extended expressions for the stiffness matrix really depends on what's the order of this interpolating polynomial that we're dealing with in constructing these expressions. So in general, if we want to come up with these expressions in a somewhat generic way for some generic, maybe relatively high order polynomial that interpolates these different values, we need some kind of generalized approach to carry out these integrals so that we don't have to work them out by hand. Okay, so with that in mind, it comes to this particular subject of how exactly do we automate the computation of integral expressions in a way that doesn't require us to work things out by hand. And the answer is numerical integration, which is really just a way of approximating the computation of definite integrals by instead treating these integrals kind of like a discrete summation of values of some function chosen at a number of discrete locations along the interval of integration. So if I had, let's say, some function f that I wanted to integrate over some finite interval from a to b, I could compute that integral by hand or do some other kind of manipulation to actually come up with what is the area under this curve, the integral of this curve. I could do that. I could come up with the analytical expression, or I can use numerical integration, which is really equivalent to saying, pick a discrete number of points. Let's call them x1 ranging from, xq, where q is equal to 1, and maybe it ranges up to nip, where nip is what I'll call the total number of integration points. So I'll pick some number of these integration points, which are just discrete positions, sampling different values of this particular function. And I can approximate the integral of this function just by choosing to sum up all of those discrete evaluations and also weight them. Assign them some corresponding coefficient or integral weight that is now basically just proportional to the width of each one of these maybe kind of windows here. So if I kind of approximate the integral as nothing more than the sum up of all these rectangles approximating the representation of this function, then I can come up with a reasonable estimate of what's the integral of this curve, what's the area under this curve as just the sum of all these different, rectangles of variable heights and widths. And if I do this, then I can get around the issue of actually having to analytically carry out this function. And all I have to do is just, decide where am I going to put these points, decide how big or how wide should each one of these rectangles be, and evaluate discrete values of this function at these corresponding locations. That's all I have to do. And that turns out to be a lot easier to do than actually analytically evaluating this integral expression. So that's pretty nice. And you're probably already familiar with some particular methods of doing this approach. Raise of hands if you've heard of either one of these approximate methods for evaluating an integral in this numerical way. Who's heard of this? At least one. Any other takers? Anybody who's heard of either midpoint rule or trapezoidal rule for approximating the integral of some curve? Some nods, I think. Yeah, okay. So a good number of you are probably familiar with this idea. The idea that let's just approximate it. Let's cut it up into some number of rectangles. In the case of a midpoint rule, that's kind of what we're doing here, where we just choose some discrete number of points, cut up this, domain into rectangles, and then choose the height of these rectangles equal to the evaluation of this function at the midpoint of each one of these rectangles. That's the midpoint rule. relatively simplistic. Alternatively, there's the trapezoidal rule, which is kind of similar, but the key difference here is that instead of treating these rectangles as having a value that's constant over its interval, instead we choose trapezoids. And we're linearly interpolating the value of this trapezoid from these discrete evaluation points. So slightly different, but the main idea is that we're just trying to get a reasonable approximation of what's the area under this curve just through these discrete evaluations. All right, these are pretty common methods, midpoint rule and trapezoidal rule, for coming up with approximate evaluations of integrals in this discrete way. But they have some limitations. While they do a reasonable job, they give reasonable accuracy for fairly general functions, they don't necessarily achieve exact integration if we wanted to, let's say, exactly integrate some polynomial or something of a particular degree. We would have to basically use an infinite number of these rectangles in order to exactly evaluate this function. And that might not sound so bad. Just choose enough rectangles and eventually we'll kind of converge to the right answer for how to integrate this curve. But can we do better? That's the question. Is there somehow an alternative to these different approximate numerical integration formulas that achieves much better accuracy or even optimal accuracy in computing these integrals using as few points as possible while still achieving reasonable accuracy and perhaps even exact evaluation of some integral of some smoothly varying function? Assuming that function can be reasonably well approximated by a polynomial, then it's possible to construct such an integration formula, and such a formula is in fact so-called Gaussian integration. Who has heard of Gaussian quadrature is another word for it, but Gaussian integration rules? Raise of hands if you've heard of this. We've hit upon a new subject. Okay, well, hopefully that's why you're all here, to learn something new. But the idea behind Gaussian quadrature is exactly to do this procedure of coming up with a better numerical integration formula that, not just converges to the representation of an actual integral of some curved function in the limit as I increase the number of discrete intervals, but in fact, for particular classes of polynomial, Gaussian quadrature, which is another word for integration, Gaussian quadrature is an optimal form of quadrature or numerical integration, which in fact exactly integrates any polynomial function up to some particular degree, where that maximal degree actually is proportional to the number of these discrete integration points that we might choose. So for example, suppose I chose the classical one-point Gaussian quadrature. And you'll notice, at least in all of these expressions, I'm actually choosing to define all these different integration formulas over a bi-unit interval, ranging from -1 to +1. This is pretty standard. This is fairly conventional. It's usually the case when you define these integration formulas to normalize the range to be between -1 and +1. And there's some reasons for that, but we'll kind of work with what we have. So there are a few different varieties of Gaussian quadrature formulas, but the basic idea is for one-point Gaussian quadrature, we approximate the integral using just a single point placed exactly at the midpoint of this interval, and the associated weight of this integral, which is proportional to the width of this particular rectangle, is simply equal to this whole width of the whole domain of interest. Or in other words, 2. So if we came up with this simple one-point Gaussian quadrature formula, it's really nothing more than the midpoint rule applied to this whole domain ranging from -1 to +1. Okay, two-point Gaussian quadrature looks a little bit different. We now have 2 points that are kind of spaced a little bit further away from each other. And you'll notice something interesting about these particular locations for C1 and C2, the locations of these particular sampling points or integration points. rather than actually saying, well, let's choose a midpoint rule where we have these two rectangles, and we'll choose to evaluate, the height of these rectangles as being right at the midpoint at each one of these two subdividing rectangles. Two-point Gaussian quadrature does divide this into two rectangles, but the height of the rectangle isn't based on the midpoint evaluation of this function, but rather on a value that's a little bit skewed. And in fact, that skewed position is proportional to 1 divided by the square root of 3. If you're curious what this value is, it's something like, 0.57 or something like that. So not 0.5. It's a little bit shifted away. But the benefit of doing this, of choosing this slightly shifted position for how we actually choose to evaluate these different values of this function to determine the heights of these two different rectangles, is that we actually get better accuracy in integrating functions. And in fact, if we follow this formula, if we chose this two-point Gaussian quadrature scheme, according to this statement that, a Gaussian quadrature formula that uses two integration points in this particular case is capable of exactly integrating any polynomial up to degree 2 n integration points minus 1. Or in this case, it would be 2 times 2 points minus 1 or 3. So I could theoretically integrate any cubic polynomial exactly just by evaluating that cubic polynomial at these two carefully chosen integration points. That's incredibly powerful. And it obviously generalizes to the case of, 3-point Gaussian quadrature, 4 points, 5 points, as high as you like. The idea is, at least in the 3-point Gaussian quadrature scheme, we would be able to integrate polynomial functions up to degree 2 times 3 minus 1, or in other words, up to degree 5. That's pretty cool. So we now have these formulas that not just converge in the limit as I increase the number of integration points in these domains. They're very carefully chosen so that they exactly integrate polynomial functions up to some specified degree. And if I know ahead of time that the function that I'm trying to integrate is itself a polynomial of finite degree, then in order to ensure that I actually exactly evaluate that polynomial, all I have to do is choose an appropriate number of Gaussian integration points, and I'll guarantee that I'm going to exactly integrate that function. And that's really powerful because obviously it means if I want to carry out these integrals and I don't want to incur any error in doing so, but I don't want to actually analytically work out the integrals, I could actually just use these Gaussian integration formulas, ensure that I get exact evaluation of the integral, and I can do it in this automated way. Really cool stuff. So that's really the power of Gaussian integration formulas. All right, so how exactly do we come up with these weird values? For example, in the case of, this 2-point Gaussian quadrature scheme, we have these weird, shifted values of, plus or minus 1 divided by the square root of 3. In the case of a 3-point Gaussian quadrature scheme, the positions of these integration points also have kind of these funny values, plus or minus the square root of 3/5. And, this one, this middle value is kind of nice. It's just right in the middle of this domain. But also, the choice of the integration weights in this particular formula was fairly straightforward to determine. We just equally divide this domain into 2 halves and then assign an equal weight or an equal width to each one of these 2 different kind of rectangles. In the case of the 3-point scheme, actually, it's slightly different, and it's unequal. These 2 rectangles on the outer edges of this domain actually are slightly smaller than this middle rectangle. So not only are we playing with the actual position of these integration points, we're also playing with the width of the integration rectangles, if you like, to actually come up with a better or optimal way of evaluating the integrals. But how do we actually determine what those integration point positions are and the corresponding integration weights or the widths of those intervals? How do we determine that? Well, ultimately, the way that you can come up with these formulas is by insisting that if I come up with some particular integration formula, let's say, in this example, we're looking to derive what is that 3-point Gaussian integration formula. I can pose this as kind of an optimization problem or a constrained problem where the unknowns of this problem are precisely the unknown or yet to be set positions of the integration points and the corresponding widths of the integration intervals, the integration weights. So if those are the unknowns, then if I have some discrete number of these unknowns that I need to solve for, I need some corresponding set of equations in order to solve for them, some proportional number of these equations. And it so happens that those equations come directly from this requirement that we impose that whatever we choose for these integration positions and integration weights, that if I use my chosen Gaussian quadrature formula in order to actually evaluate polynomials up to some kind of chosen degree, that I should get an exact result. So in other words, if let's say I were to integrate a constant function, in other words, if I were to integrate a polynomial of degree 0, so consider c taken to the 0 power, which is just equal to 1. So if I'm trying to integrate a constant function, that's equivalent to just saying integrate some function, which is everywhere equal to 1, sum up all of those discrete evaluations of this function over the interval, which is proportional to just 1 times the individual weights of that function at these different quadrature point locations, sum it up, and what I should get should be exactly this expression that I have here. And that should be true up to whatever polynomial order my quadrature rule needs to exactly integrate. So if I have this 3-point integration formula, then according to my rule, I should be capable of integrating up to polynomials of degree 5. So quintic polynomials. So if that's the case, technically, I should have really 5 of these equations that I have to satisfy. But I've been a little bit funny in how I've chosen to pose this problem. Rather than saying there's 5 equations that I have to satisfy, technically there's 6 of these unknowns, 3 integration point locations and 3 integration weights that I have to solve for. So there's really 6 unknowns, but I've reduced the size of the problem by noting a few things. First, by saying I'm going to choose an integration formula that is symmetric. That is to say, whatever points that I have on either side of this domain reflected about this kind of value of c equals 0, I'm going to insist that the integration points should be spaced in a way that is kind of symmetric with respect to this domain of interest. So in other words, c1 should really be equal to minus c3 in order to ensure that symmetry. And I also insist that this width of this integration domain should be the same as this width. So in other words, w1 should be equal to w3. So that kind of reduces things a little bit further. I can also use symmetry to argue that the position of C2 should be right in the middle. If it was shifted a little bit left or right, it certainly wouldn't look symmetric. So we have to insist that that's the case. In doing so, we reduce the number of unknowns we have to solve for down to just these 3 unknowns. The 2 weights for this width, and the position of integration point 3, or equivalently integration point 1. Now, it turns out that if I impose those constraints, then all of the odd polynomials that I would try to integrate actually produce a rather trivial result. Integrating odd polynomials is just equal to 0. So I don't really get any good information out of trying to integrate odd polynomials. It's really only the even polynomials that give me any information that I can work with. And these 3 even polynomials, c to the 0, c squared, and c to the 4th, actually give me precisely those 3 equations that allow me to solve for these 3 distinct unknowns characterizing this integration formula. And I can proceed in actually solving for the unique values of these different things, first by noting that the first of these 3 discrete equations gives me a way of expressing the value of this second integration weight in terms of the third integration weight. And also I can note that by combining these 2 expressions that were determined based on the integrals of c squared and c to the 4th, that if I divide this expression by this expression, giving me something that looks kind of like this, then the terms involving W3 cancel out, and all I'm left with is C squared, or rather C3 squared. I can use that fact to actually directly solve for what the value of C3 is, and then through an additional step, I can come back, plug in this known value for C3, figure out what the value of this third integration weight is, and then subsequently use this expression to determine what's W2. So voila, and I exactly recovered those expressions that I showed previously. So really, Gaussian integration, by construction, in fact, satisfies this condition, that it exactly integrates polynomials up to maximal degree 5. All right, very cool, very cool. All right, and what's really the benefit of this? Well, as I mentioned earlier, things like midpoint rule or trapezoidal rule, technically speaking, they do converge as you increase the number of integration intervals that you're using to approximate the value of the integral of some function. As you increase that number of intervals, you do reduce the error that is incurred by approximating the integral expression in the limit. But it's not exact, and you'll never technically get there. It'll take an infinite number of these intervals to actually get the exact value. By comparison, an endpoint Gaussian quadrature formula gives you the exact result up to, integrating polynomials of degree 2n minus 1. So very useful if you know that you're integrating a polynomial of a finite degree, and that really comes to bear in solving these finite element problems, where we know that if we're treating these particular functions of interest, the interpolated representation of the displacement field as some polynomial interpolating function, then I know that the resulting integrals that I get in solving the weak form and assembling these finite element stiffness terms, that they will involve integration of some set of polynomials of finite degree, in which case using Gaussian quadrature formulas is really the right solution. Okay. Now, the other nice thing about Gaussian quadrature formulas is that they don't just apply in the case of, let's say, these one-dimensional problems where we want to integrate over this one-dimensional domain, some function that varies as a, variable, function of position C. I could also generalize this concept to say, let's not just put points down on a one-dimensional line to evaluate some integral defined in one dimension. I could also come up with quadrature formulas defined over two-dimensional domains or three-dimensional domains by extending this same concept. And in doing so, I actually ensure that even though this domain is much more complicated in 2 dimensions, it gets worse in 3 dimensions. Assuming I choose a sufficient number of these integration points placed at these strategically chosen locations and weighted by these appropriately chosen integration weights, I nonetheless ensure that I'm going to be able to exactly integrate polynomials over this square patch, let's say, exactly, which is incredibly powerful. We won't actually get to the subject of evaluating integrals over these kind of 2D or 3D patches until a little bit later. I wanted to come back and kind of reconcile how exactly do we use Gaussian quadrature in evaluating stiffness matrices in just this one-dimensional context first, to connect it back, to show you what's the utility. All right, so remember, in the case of one-dimensional finite elements, we came up with, in the previous lecture, I believe it was, this definition of finite element basis functions. And more specifically, if we were looking at a particular element, within that element, assuming it's just an element that consists of 2 nodes, so not this situation, but rather this situation, where I have just 2 nodes at which I have discrete values of displacement, or if I like, I can also choose to represent, just the discrete values of nodal position, x1 and x2. And the idea is I can choose to represent whatever function, the displacement field, or even just the position of points arranged along the length of that element, in terms of just some linear combination of these local element basis functions, sometimes also called shape functions. So if you hear me say the word shape function, Really, I'm referring to nodal basis functions that are local or specific to a particular element of interest. So in the case of this one-dimensional problem, the shape functions are really just these two basis functions associated with the two endpoints of this, particular element that I'm looking at. All right. So if I wanted to represent the interpolated displacement field expressed in terms of U1 and U2 defined over the length of this element, I could plug in U1 times N1 plus U2 times N2, and I would come up with some interpolated representation for the displacement field over the length of the element. Alternatively, I could also interpolate the nodal position field, X1 and X2, over the full length of this element. And in doing so, I actually come up with X as a function of this local element coordinate, which I'm calling Xi, where Xi ranges over this normalized coordinate range from -1 to +1. And we do this partly to reconcile some of those issues that we kind of alluded to previously with having our integration formulas also defined over this same range from -1 to +1. You'll see why that's kind of relevant in a minute. But the idea is we have these basis functions or shape functions, N1 and N2, themselves just linear functions. N1 is a downward sloping linear function with a value of 1 at c equals -1 and a value of 0 at c equals +1. And N2 is a similarly upward sloping function that kind of satisfies the opposite. If we combine them, we can represent any linear function, which also passes through these two discrete nodal positions, X1 and X2. Now, what's interesting is I could represent X as a function of C, or I could actually invert this relationship and write it the other way around. I could instead choose to write C as a function of X, which is kind of equivalent to taking this graph and then mirroring it so that we're kind of looking at it actually from the side. So rather than having C on this coordinate direction, X on the vertical direction, now I flip it. So X is on this kind of horizontal direction, C is on the vertical direction, expressed as a function of X. Either way, we can kind of go back and forth between the two because we recognize that this function is invertible. It's a one-to-one function. So if we wanted to invert this mapping, going from the local element coordinate C into a representation of the global coordinate X, or if I wanted to go the other way, if I wanted to represent the local element coordinate C in terms of the global coordinate X, I could do either one of these two things. But in the end, I can kind of go back and forth between them. All right, so we have a relationship now between this local element coordinate C and the global coordinates of points maybe oriented along a given element of interest. And that mapping between those two different domains of interest, between C ranging from -1 to +1 and X ranging from X1 to X2, having this mapping, sometimes also called the isoparametric mapping between these two different coordinate domains, is incredibly useful if we're trying to convert integrals defined over C ranging from -1 to +1 into equivalent integrals defined over X ranging from X1 to X2. The critical piece of the puzzle that we have to supplement is, well, actually a couple things. The first thing that we need to do is recognize that these shape functions, N1 and N2, are expressed not in terms of X, but rather they're expressed in terms of C, the element's local coordinate system. And that poses a problem because at the end of the day, all of these weak form integrals, the things that we need to integrate to come up with stiffness matrix computations, involve the derivatives of the shape functions with respect to X. However, we haven't defined these functions with respect to X. We've defined them with respect to C. So therein lies the problem. How do we get around this problem? Well, the solution is, if we want to compute the derivative of, let's say, N1 with respect to X, we can actually use the fact that, well, I could actually just say that N is a function of C, but C can equivalently be represented as a function of X. So by the chain rule of differentiation, I could equivalently evaluate this derivative as first taking the derivative of n with respect to c, and then taking the derivative of c with respect to x. And in doing so, the product rule tells me I just need to take the product of those two things, and I get back to exactly the derivative of the shape function with respect to x, the global coordinates. It turns out that if I take first the derivative with respect to c, that's basically derivative of n1 with respect to c, just gives me minus 1/2. Derivative of n2 with respect to c gives me just plus 1/2. So those are pretty easy, and they don't depend at all on the length of the element at all. If I wanted to compute this thing, derivative of c with respect to x, now I have to come back to this expression and see, well, what happens if I take the derivative of this thing with respect to x? And what I get is 2 divided by x2 minus x1. In this case, this derivative expression actually does depend on the length of the element. So there's an interesting dependence there. I can call that length x2 minus x1 just L sub e, referring to the length of that particular element e. All right, composing these things through the chain rule of differentiation, I finally come up with this expression that basically says that the partial derivatives, or the derivatives of n1 with respect to x and n2 with respect to x, are really nothing more than plus or minus 1 divided by the length of the element. Okay, so that was essential. And now the last step. How do we actually transform these integral expressions that ultimately look something like integrate some function f expressed as a function of x, the actual global coordinates, taken with respect to x ranging from x1 to x2. What we want to do is transform these integral expressions, which are kind of equivalent to integrating these terms that show up in the stiffness matrix. We want to transform this integral into something that looks more like everything expressed and defined relative to the element's local coordinate system, that c ranging from -1 to +1. And to do this, we actually have to use something called a change of variables formula, which is really nothing more than just saying, well, if I want to evaluate f at x, assuming I have an expression for x as a function of this local coordinate c, then all I have to do is just plug in that expression, and I can come up with an equivalent expression for this function, just expressed instead in terms of c. That's simple enough. But in order to change the domain of integration, to change dx integrated over x1 to x2, I actually have to come up with some replacement for dx. And it turns out it's not so different from what we looked at previously when we were looking at the chain rule of differentiation. All I have to do is just replace dx with the derivative of x with respect to c times dc. And in doing so, I can basically just plug that in and instead define the integral to be ranging over c from -1 to +1. So that's really the critical step. If we do this and apply it precisely to this definition of integrating the element stiffness terms, what I find is I can take all those previous expressions that I derived for the derivatives of the shape functions with respect to x. I can use the chain rule of differentiation to express those as the derivative of the shape functions with respect to the local element coordinate c multiplied by the local coordinate c divided, partial derivative with respect to x for both of these different shape functions appearing in this term. And I can substitute integration over x in terms of an equivalent integration over c, where I have to introduce this additional derivative of x with respect to c. Subbing all those things in, I finally get an expression that's expressed entirely in terms of the element local coordinate system, c, ranging from -1 to +1. And now I can use my integration formulas, my trusty Gaussian integration rules, which in the particular case of this simple one-dimensional finite element that just has, a linear interpolation of nodal displacement using these simple shape functions, I notice that really these resulting expressions for the derivatives of n1 and n2 with respect to c, that those expressions are just constant values. So if I'm trying to integrate some function that basically is just involving the integrand being a constant value, I don't really need anything fancy. I could just use a one-point Gaussian integration rule, and it will exactly evaluate this expression. It's not just approximate, it's exact. So if I choose this one-point Gaussian formula to integrate this expression, choosing my integration point positions to be placed right at, c equals 0, and the integration weight being proportional to the width of this whole interval from -1 to +1, what I come up with is this final expression. Evaluate this integral just through discrete evaluations of the integrand at this particular quadrature point location, c equals 0, and weighted by the integration weight 2, I come up with this expression, which is really just a bunch of different constant values of variable sign. In the end, I can put all these things together into the format of this small 2x2 matrix, or the element stiffness matrix, which if you went through the homework number 1, then you likely recognize what this looks like. It's just E times A divided by L, the stiffness associated with that element, and then a small 2x2 array consisting of plus or minus 1. Plus 1 on the diagonal, minus 1 on the off diagonal. So that's a lot of work to get to this final result, right? The thing that we basically came up with in the second lecture in this class. But really, the power of this is that it generalizes to any arbitrary choice for how we choose to represent these interpolating element level polynomials. And that's really the utility. It's also really useful when we try to generalize these same concepts and apply them to not just one-dimensional elements, but elements in 2D and 3D to represent solids. So that's where we're going with this. And it's kind of a little bit of a heavy-duty subject, but eventually we'll kind of come to this subject and, utilize these resulting expressions to say, all we have to do is just compute the element level stiffness matrix terms, enter them into these kind of appropriate locations in the stiffness matrix, and then sum them together. So really nothing more complicated than that. All right, that's all we have time for today. If you have questions, feel free to visit me in office hours. Otherwise, I'll see you on Wednesday.